Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is heap sort, and it is a medium level problem. So if you are a computer science student and you already had your algorithms course completed, then you must have definitely studied this particular algorithm for heap sort. In our engineering programs, like this is one of the most standard things that is included in the syllabus. So if you are already aware, then well and good. Otherwise, I'm just going to explain you what is heap sort and how are we going to perform it. So the question is very straightforward. It says that we have been given an array of size n, and our task is to sort the array elements by completing these functions heapify and build heap. Right. So basically, we have to perform heap sort and we have to call these functions. Now the input is not very difficult, just an array, and we have to return the output. Let us see how we can solve this particular problem. So before solving the problem, we will have to study a lot more about heap sort or how it is performed. So if you have been given an array like this, let's say this is an array. In this particular array, there will be some indexes. So this is the 0th index, this is the first index, second, third, fourth, fifth, sixth, seventh, and 8th. So let me write it again. This is 6th. Right. So first of all, I want you to visualize this particular array in the form of a tree. So let's say this is the root node or the 0th node. Right. Now the left child will be 1 and the right child will be 2. Right. Now the left child of 1 will be 3 and the right child of 1 will be 4. Similarly, the left child of 2 will be 5 and the right child of 2 will be 6 and the right child of 3 will be 8. So these are all the nodes or all the elements that we have in the array. Now, once you visualize this, first of all, let me discuss how are we deriving the left and the right child for each of the nodes. So if you have observed that if I have a current node, its left child, I am denoting it by LC, left child will be equals to node into 2 plus 1, and its right child will be denoted by node into 2 plus 2, right? So if I want to find the parent of any node, I can find the parent of any node by doing node minus 1 by 2. So these are the relationship between the indexes of any two nodes, right? So if I have a node, it will be connected to three other nodes, that is, one is the left child, one is the right child, and one is the parent. So I hope that you guys were able to understand this relationship between these nodes, right? So these are nothing but the same array indexes. It's just a way of representing the same array in a form of a binary tree, right? So you see, the left child is represented by twice of node plus 1, the right child is represented by twice of node plus 2, and the parent is represented by node minus 1 by 2. So let us look at some examples. Let's say I am taking node 7 and 8. I want to find its parent. For node 7, it will be 7 minus 1 by 2, that is 6 by 2, and that is going to be 3. So the parent of node with index 7 is going to be the node with index 3 or the array element with index 3. Similarly, I do the same thing for 8. So 8 minus 1 by 2, which is equals to 7 by 2, which is equals to 3 as well, right? So we are taking the floor value, which will automatically be obtained by normal division, right? So now I have established what is the relationship between the nodes and how we can find the left child, right child, and the parent. So now let me just explain you the whole concept with the help of a tree, and then we will try to convert it into an array form. So let me just take an example. The array input is 4, 1, 3, 9. We're going to discuss this particular test case. So there are actually some technical terms used in heap sort like build heap or heapify. So we are going to discuss what are those terms used for. So first of all, I would want to build my heap. Building my heap means that I want to build a tree out of these elements, right? So let us see how we can build a heap. But before that, we need to know some properties of heap. So there are actually two types of heap. First of all, there is a max heap and then there is a min heap, right? So if I try to write it in short, then I would write parent is always bigger, right? And if I try to write the property of min heap in short form, then it will be parent is always smaller. So smaller in comparison to what? in comparison to their children, right? So if I'm talking about a max heap, the parent will always be bigger than their children, and if I'm talking about a min heap, the parent will always be smaller than their children, and this will help me to sort the array in ascending order, and this will help me to sort the array in descending order, right? So these are the two important properties of heap, and keeping in mind these properties, we are going to build our heap or build our binary tree. Now we're going to build a max heap. So first of all, I encounter a node 4, right? So I can just insert 4 here. So I've inserted my first node 4 into my tree. Now my next input element or the array element is 1. So the next free position is this one. I inserted at this particular position. Now if I was building a max heap, I need to check whether there are any places where the condition of max heap is not satisfied. So in this particular case, all of the parents are bigger than the children. So every condition is satisfied. There is no problem here, right? Now I insert my next node 3 here, right? Still there is no problem. Now my next node is 9. So I need to insert 9 here. Now you will see that my current node is actually smaller than its parent node, which should not be the case in a max heap. The parent should always be bigger, right? So I need to do something about the situation. What I can simply do is I can take this node and swap it with its parent. So this 9 can come here and this 1 can come here. Now the next thing I would like to do is check whether this node is still greater than its parent or not. So I see again this particular node is greater than the parent node. So I again need to make a swap, right? So now the node 9 comes here, node 4 comes here. Now I again need to check whether this node is greater than its parent or not. But I see that there is no parent for this particular node. So that means I cannot perform any operation further, and this is my desired state of a heap, right? So let's say the next element, let me just change this element, let me take just 5. So the next element 5 will be inserted here, and can you observe this fact that I am only inserting the nodes in level order traversal. That means I want to complete at each level, I want to complete the nodes from the left side only. So you have to maintain this property, and this property of a binary tree is also known as a complete binary tree. So a heap has to be a complete binary tree, right? This is one more thing that you need to keep in mind, that your heap has to be a complete binary tree. That means whenever you are inserting node, so let's say you have completed this 0th level, this is first level, you are at the second level now, you cannot insert nodes anywhere. You have to insert it from the left, right? Only then it will be called a complete binary tree, right? So now when I insert this node 5, now I want to check whether there is any violation of properties. So I have made sure that it is a complete binary tree because I am inserting it the leftmost position possible. And now I need to check this particular condition of max heap, that if my parent is bigger than my child node or not, right? So 4 is bigger than 1, that is good enough, but 4 is not bigger than 5. So I need to swap these two nodes. That is why I just make 5 here and then 4 will come downwards, right? Now I again check whether this node is greater than its parent or not. So if this element is greater than its parent, I need to pull up this node, but since it is smaller than the current parent, that means I can stop my call here, or I don't have to move any further. So you see, I have finally built my heap, and this heap is going to help me to sort the elements. So this part, what I have done here, is actually known as build heap, and all of the things that I do to make sure that the properties of a heap is satisfied is called Heapify, right? So this Heapify, what this does is, the core functionality of this function is to make sure that none of the properties of a heap are violated, and whenever I insert a new element, the new tree that is formed should follow the properties of a heap. This build heap function will help me to basically build my heap. So these are the two important functions here. Now since I have built my heap, the question is, how do I sort the elements, right? So you will observe, because of the property of the heap in a max heap, the top element is always going to be the greatest element, right? So the top element is always going to be the greatest element. Now what can I do with this property? Let's say there were 5 elements here, so I am going to create an array of size 5, right? Now what I do, I'll try to pop my first element and remove it from the heap. Since I've constructed this heap, let me just try to rearrange the same heap in the form of an array using the properties of relationship between nodes that we have studied earlier. So 9 is a root node, so it will be positioned at index 0. Now its left child is 5, so its left child should be at 0 into 2 plus 1, that is index 1. So 5 should be present here. The right child of 9 is 3, so it should be present at 0 into 2 plus 2, so it should be present at index 2, so 3 is here. The left child of 5 is 1, it should be present at index 1 into 2 plus 1, that is 3. So at index 3 we have 1. Now the right child of 5 is 4, so it should be present at 1 into 2 plus 2. So it should be at index 4 and we put 4 here. Right. Now since we have all the elements, this is the same tree that is being represented by our heap. Right. Now I want to pop this topmost element. Right. I want to pop this element and store it somewhere. Right. So if I want to sort this array, I would always want the element at the 0th position to go at the last position possible. Right. Please understand what I am trying to say. I've already made sure that my 0th element is always my greatest element because it is a heap and it should be satisfying the properties of a heap. Now I want to take this element and I want to put it to the last position possible. Right. So I put it in the last position. But I cannot just directly put it. I also want to preserve this element. So instead what I do, I just simply swap their positions. Right. So let's say 9 will come here and 4 will go at the first position. Right. As soon as I do this, let's say I am also updating it here and 4 will come here. As soon as I do this, my current heap or my current binary tree is not satisfying the properties of a heap. So what do I do now? I want to make sure that it still satisfies the properties of a heap. So I want that this position should be taken by the maximum element. Now what I do, I will check what is the left child of the current node and what is the right child of the current node. Whichever of them is greater, I'll consider that. So in this case, 5 is greater. So let me just say that C1 is greater than C2. So C1 is child 1 or left child and C2 is child 2 or right child. In this case, C1 is greater than C2. So I'm going to take C1. Right. Now if the value of C1 is greater than my node itself, that means this is the deserving candidate that should be present at the current position, right? Because this is greater than the node value. Now if it is greater than the node value, I'm going to swap this particular 4 with this child C1. So 4 will come here and 5 will come here, right? Now if it was the other way around, that C2 was greater than C1 and C2 was also greater than the node value, right? Then in that case, I would have swapped the current node with the right child. Now there is a third case as well, when let's say either C1 is greater than C2 or C2 is greater than C1, but the maximum of them, maximum of C1 comma C2 is still less than the current node. That means my current node is the maximum and I don't need to push it down, right? So basically I'm trying to take the maximum element and place it at the current topmost position. So if I do this operation, I swap 4 with 5, what will happen? You will see 5 will come here and 4 will come here. Now again, my property of heap is satisfied. So my biggest element or my greatest element will be present at index 0. Now, since I have already placed my last element here, so my last available position is now this one, right? This position is now fixed. I would say this is fixed. So I cannot put any element here, but I can put an element at this particular position. You do the same thing again, you just swap the elements of these two positions. So 5 will come here and 1 will come here and this will also get fixed. Let me just also update the binary tree. So 5 will come here and 1 will come here. Now I repeat the same process again. I want to shift elements down, right? I check which of the child is greater. So C1 is greater than C2, 4 is greater than 3. I check whether C1 is greater than node, 4 is greater than 1. Yes, so I need to swap these two elements. I swap 1 here and 4 here, right? So let me just perform the swap here also. So 4 will come here, 1 will come here. Now you will see that they still have their children. Now this node 1 still has some children. Both of them are greater, but I'm not going to swap in this case. Why am I not going to swap? Because these two positions are now fixed. You see that 5 is fixed, 9 is fixed. So I'm not going to consider these elements while swapping the node. So I've represented it in the tree because these nodes will actually be still present in my array. But since these nodes are already fixed, so I can also delete them, right? It is the same as deleting, but since they were already in the array, that is why I was representing them in the binary tree as well. But in a sense, when we talk about a real heap, they are actually deleted from the tree, right? Now we are remaining with these three elements 4, 1 and 3. So the next step I do is I take the 0th index, I take the last possible position, I swap them. So 3 will come at this particular, position, 4 will go to its place. Now this position is also fixed. So now let me just convert this. So the only two nodes remaining is 3 and 1, right? Now 3 is greater than this child node, so I don't need to perform any swap. The next step I do is swapping the positions. So 1 will come here, 3 will come here, this is also fixed. And this, since there is only one element remaining, I don't need to do anything. If all the other elements are sorted, the first element will also be sorted, right? So all of the positions are now fixed. So I'll tell you a quick summary. The core idea is to try to maintain the properties of a heap. We want to maintain that it is a complete binary tree, and in case of a max heap, I want to make sure that the root node is always greater than its children, right? Every node should be greater than its children. Now, how do I satisfy this property? As soon as I insert, let's say this is a node, right? As soon as I insert a new node, I want to make sure that this node is in its correct position. So I usually call this pull up. You can also call this pull up, because what we are doing, we are taking this node and pulling it up towards the root node, right? So whenever the current node is greater than its parents, I'm going to pull it up in the tree. Now when I want to delete a node, what I do, I have a tree like this, right? So now I take this element and put it at this particular position, and this element will go upwards. So in a real tree, I'm actually deleting this node. So the bottom node will take its position here, and this node will be completely deleted. Now what I do, I call this technique push down, because what I'm doing, I'm checking whether any of its children is greater than the current node. If the children are greater, I need to push this element down the tree, right, away from the root node and down the tree. So these are the two things that you need to consider while solving this particular problem, and these are the two things that you need to know. So now everything that I explained here, the relationship between the nodes will come to use now, because we have studied how to perform all the operations in a binary tree. But how do we perform these operations in the array? How do we find which is the parent, which is the left child, which is the right child? So we are going to find them using these properties or these rules. I'm going to show you the code and take this thing with you. You can write it down and then you can relate what I'm trying to do, because it will be much easier for you to understand the actual implementation with the help of the code. So let me just open my final summation code. So you see what I've done is, first of all, this heap sort function will be called by the main function. So I have called my build heap function here. Now build heap is going to one by one insert all the elements in my heap. So I'm starting from the 1th position and I am going till I less than n. So actually the 0th position, I don't need to do anything, because as you have already seen in the explanation, when I insert the first node, there are no changes to be made, right? So I'm starting from the node which is at the next one or the second node. I call my Heapify function, which will make sure that all the properties are satisfied. So now what I do is, I am storing the value of the current node in my variable current or CUR, and I am storing the value of the parent node in the value called parent, right? So there are two conditions now I need to check. While I is greater than 0. So what is I? I is the index of my current node. Current is the value of my current node, and parent is the value of the parent node, right? So remember, these two are denoting the values, and I is denoting actually the index in the array. So while I is greater than 0, that means while it is not the root node and my value of parent is less than my value of current. So what I'll do, I'll swap these two positions. This is the position of the parent, this is the position of the current node. After I've done this, I'll update the value of I by I minus 1 by 2, right? Now I'll update my value of current as array of I, and I'll update my value of parent is equals to array of I minus 1 by 2, right? So these are just updating values, and I'm going to do this part only when I is greater than 0, so that it does not go negative, right? Now after all of this is done, after I've built my heap, what I'll do, I'll set my last position as n. So in the last variable, I am storing the position that is not allowed. Remember, at the last variable, I am storing the position that is not allowed. So initially, n will be out of bounds for the array, and since all the positions from 0 to n minus 1 are available, so that is why n position will be not allowed. While last is greater than 0, while my not allowed position is greater than 0, I am going to swap array of 0 and array of minus minus last. So what am I doing here? Since n was not allowed, so the first position that I could have inserted in element was n minus 1. That is why I am decrementing it here. I am doing pre-decrement and I am swapping these two positions. Now I am going to start my index with 0 because this is my root node and my value of the starting node will be equals to current. So this is array of index. Now I am creating two variables C1 and C2. This is going to denote the value of the children. So C1 and C2 both will be equals to minus 1 initially. Now if this left child is less than last, that means this left child is among one of the available positions, that then I'll update my value of C1 and similarly I'll update my value of C2. So remember, this condition is very important. I need to update my value of C1 and C2 only when the position that is being denoted by them is actually a valid position and not a fixed one. So that is why I'm checking this condition. While this position is less than last, I'm updating C1 and C2 respectively. Now I'm creating a while loop while C1 is greater than the current value or C2 is greater than the current value. If either of them is true, I need to make a swap, right? So I check if C1 is greater than current, right? If C1 is greater than current and my value of C1 is greater than C2, that means the C1 is greatest of them all, right? I'm checking both of these conditions. Now in this case, I swap the current index that is represented by IND by index 2 into 2 plus 1, right? So this is my left child and I update my current index as the index of the left child. Simple. Now if this condition is not satisfied, I check whether C2 is greater than current. So why else if? Because either one of them was true, right? If this is not true, this must be true. So in that case, I am going to swap these two positions and I am doing array of index into 2 plus 2. So this is going to represent the right child and I am swapping it with the current index. And I update my current index as index into 2 plus 2, which is going to represent my right child. Now I again initialize my value of C1 and C2 with minus 1. I try to find the left and the right child respectively. If they are not among one of the fixed positions, I'll update the value of C1 and C2 respectively. Right. So this all is all about the problem of the day. So since the input was passed as an array, the updates will be made automatically on the initial array itself. So I don't need to return anything. Let me just submit this and show you that this particular code works and this solution is absolutely correct. So you see, it passes all the test cases and this is correct. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video and don't forget to share thoughts in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you and you'll be able to reach more number of people like you who want to keep solving new problems. So I see a lot of people who watch these videos have not subscribed yet. In case you're one of them, then definitely consider subscribing. It's always free of cost and you can always unsubscribe if you don't find the videos interesting later. So share this channel with your friends. Until the next video drops, keep coding, stay safe, bye bye.